Okay, this is the chapter 1 of the IPS, the planning and the power demands for the BEV 4023 industrial power system. And as we have described in the RPP04 or lecture plan, so we have 5 subtopics to be covered in this chapter 1. So actually this is just a recall, whatever you have learned previously. And this is the first introductions to the IPS. Where is the IPS is located in our electrical power system? We have the generation systems. Normally the generations is about 15 kV, right? So the generations kV is about 15 kV, and then it will be step up using the transformer here, right? Then it will go to the transmission system, and the transmission system, the highest in Malaysia is 500 kV. Right now is 500 kV, which is near to the Jana Manjong, Perak, right? You go to the Batu Gajah, then you can see 500 kV, and then finally you will go to the distribution system by using the step down transformer here. And where is our industry partner here? So this industrial customer. So industrial power system, normally the kV size is from 11 kV to 275 kV. So it's 275 kV is for a very huge or a very heavy industrial consumer, right? So this is for us. This is a residential consumer, a resident consumer. So if the heavy industrial, they will have the power directly from the transmission system, and they will have the power directly from the transmission substation. It is not from the distribution, so it's only less than 66 kV. If the kV requirement for that particular factory is between 11 kV to 66 kV, then they will have the power from the distribution substations. Okay, so this is the overall. Okay, when we enter the factory, so of course this is some sort like the TMB. So we have the transmission system, and then the first things you need to design is the distribution transformer. This one, right? The distribution transformer. So it's very important. So this is a very costly, very costly. So a small IPS, normally they will have maybe a few hundred kVA. For the huge industrial consumer, they will have up to several MVA. So they have a 10 MVA, 20 MVA, or 30 MVA, and etc. And it is not only one piece of the transformer, distribution transformer. They could have a few pieces of the transformer. It depends on the design. That means the network layout design, layout design. So after the transformer, so let's say we take from 33 kV, 33 kV. So we step down to 11 kV, for example. This is the step down transformer. So from 33 to 11 kV, and then the first it enter is the so-called switch gear. So this is a switch gear. So in this case, they are using the switchboard because this factory is a smaller factory. This is the whole factory, the building of the factory that you can see here. Okay, so if the smaller one, they use the switchboard. The bigger one, they normally use the switch gear. Then the switch gear is the a cubicle that distribute the power to the rest of the factory. So for example, so you have another distribution board here. So you will serve the common power applications, and common power applications like the lightings. You have the sockets and the plug, and then you have the computer, and you have the air conditioner. Okay? And another one, it could be go to the load center, and the most common in the factory is one of the distribution is going to the MCC, the motor control center. So at this cubicle, this is the metallic cubicle, so that's serving a group of the a motor. So of course inside here you have the drive, and I mean you drive the motor, how to control the motors, how to stop and how to start the motor. So everything will be done here, including the PLC. So if you have the PLC, then the PLC will be packed inside here. Okay, and of course if you have a very large pump, for example, right, a lot of the factory they are required to have a water pump, right? The water pumps to have so many applications to have that water pump, and then this water pump is normally is a quite huge pump. It's normally it is more than 100 horsepower up to maybe 1000 horsepower. Okay? So that's why if a huge pumps, that means we have to lead the cables directly from our incoming here, right? That means the incoming from the switch gear directly, so we don't tap the power from, let's say, the MCC or the distribution board here, right? So that means it need more protections, because this one will draw a lot of the currents, and it might be disturbs the rest of the load. Okay, the plannings, the power system concepts normally implied by the name, the power system and the whole system, and actually it is for the analysis, and selection of the network configuration was also important in the power system concept, and the type of the grounding, also included in the power system concepts, including the technical features of the power system. So we need to have some knowledge about the technical features that available in the power systems. And then once we have the power system networks, so what can we do for the calculations? Normally is the load flow. So this one is a must in the power system. So we have to analyze the load flow first, so that we can know the flow of the P and Q in our power system network. And another thing is we try to analyze the short circuit calculation. And why short circuit calculations? Because every network in the factory, so we will have limitations. We have limitation in terms of the short circuit capacity. I mean, in terms of the short circuit capacity, the larger the short circuit capacity, that means the more stable that your power system is. That means the larger the short circuit capacity of your plant, that means the more stable of your power plant. That means if any fault happens, a small fault happens, so it won't trip the whole factory. Unless your short circuit capacity is very small, then you have a big problem on that. Even though a small fault also will trigger to the blackout. So that's why the short circuit calculation is very important. And the next is energy balance. So we try to balance up the energy. So we have three phases, right? Three phases, the RYB, red, yellow, blue, and then we try to make these phases as balanced as possible. So otherwise we'll have some problem like the voltage drops, right? So if one side, let's say R is very heavy, if compared to the Y and B, so that's why a lot of the issues will be happen at the red color phases. And regarding to the ratings, so we just wanted to know some ratings in our IPS. For example, the transformer, what is the rating of the transformer, how many kVA or how many MVA, so what is the voltage supply there, and cable size. So is our cable is underground or we laid overhead, I mean on ground or underground. Okay, another one is the protective devices or the switching devices. The switching devices is such as the power factor corrector. So power factor corrector is one of the switching devices. We try to switch on and off frequently just to inject the required reactive power, so that we can adjust the power factor. So that is one of the switching devices, the power factor corrector. And the provision for the redundant supply is regarding to the UPS, for example. So we have the backup supply. So we have the UPS, uninterruptible power supply. So that is the ratings that we need to consider in the IPS. So we have the residential, right? We have the commercial, right? The medical, like hospital, is the commercial building, right? The commercial building. So what we concern now is the industrial. Then we try to look at the features of the IPS, industrial power system. Eh? So the feature is, one of it is mainly modal loads. So that means we have a lot of the modal loading in the IPS. Okay, so that means the requirement is they have to have high power quantity required per area. That means one area. So let's say normally it will calculate based on the meter square, the meter square. So 1 meter square, okay, how many power, how many kVA you need. So that is so called the high power quantity required. So that's why if compared to the rest of the residential or the commercial building, so the industrial power system is required higher power quantity per area. So that is the feature, and the actions is we need to install a bus bar trunking system, right? Because in the house we don't have the bus bar trunking system. It's a very big bus bar trunking system, right? So what we have is just some cable, right, from our DB. Okay, the minimized downtimes, so it's very crucial in the IPS. So we try to minimize the downtimes, so otherwise it will disturb the production. It will disturb the production. So that's why we try to minimize the downtimes, which is the blackout. Okay, so the higher reliability of the supply. So that's why in the designing of the IPS network itself, so you need to consider this. Okay. So it's not all the design is good, and not all of the network design is good. So you have to design it according to the needs of the IPS. This is why you might experience it in your maybe in your project. Okay? So that in order to make our networks more reliable, so we need a redundant supply. We need a UPS. We need a backup supply. We need a backup generations. Okay, or sometimes we call it as a captive generation. Captive generation is the a backup generations. For example, you have the diesel, you have the renewable energy, right? So you have the solar, and so that is so called the captive generation. The captive generation. And we have the process, a different process, a lot of processes in the industry, from the manufacturing, from the productions to the workshops. You have the workshop, you have the laboratory inside the in IPS. Of course, you have the normal offices, the offices in the factory. So that means a lot of the patterns. They mean in terms of the power usage. So many different patterns of the power usage, or we call it as a different processes. That's why we need to have a very nice selective grading. Later on we'll see what is the selective grading, and how to select, how to choose the proper installations of our transformer, for example. Okay, why we need to plan our distribution systems? So the major objective or the major goal is to optimize our network. Optimize in terms of the cost, optimize in terms of the reliability supply. So this is the two main things that we need to bear in mind when we plan the IPS. So of course we need the simplicity, the simple structure, as simple as possible, so that we can do maintenance well. So the high reliability of the supply. So if we have a very limited supply from TMB, why not we introduce the backup or renewable energy, for example, right? And the low losses. You need to deal with the design of the power cables. So don't oversize the power cable. Right? So if you oversize the power cables, so one is you waste a lot of money, another ones you have might be the losses. Let's say this is not oversized, this is the undersized. If the power cable you design is undersized, so that means you will experience a lot of the losses. And variable and flexible of the expansion. So of course when you design for the IPS, so you need to think following the standards, the code of the practice. So for the IPS, so we need to have some reserve or spare, as what you have learned in the utilization. So when you design for the electrical network for house, for example, so we need to have at least 10%. But for the IPS, the percentage is between 15 to 30%. 15 to 30%. That is following the standards, the standards of the electrical installations. For the IPS, we need to have some expansion options, or we call it as a spare, the spare for 15 to 30%, right? And this is what you can see from the IPS. So you have the switchgear. Switchgear is the inside the switchgear we have the transformer as well. We have the transformer which might step down further. Let's say just now we have the distribution transformer step down from 33 to 11, and then if we have the application in the factory, let's say we have another kV, we have 6.6 kV, for example. So where can we get the 6.6 kV? From 11 kV we need to step down further, right, to 6.6 kV or 3.3 kV. So this transformer is located inside the switchgear here, right? And the switchgear is it will distribute all the powers, all the powers into the building. So this is all inside the building already. So all inside the factories. So you have the switchboard, you have the panel board, which is the smaller board, DB, the panel boards, which control parts of the load center in our factories. Alright, distribution. The distribution system normally we deal with the distribution of electrical energy, and we need to make load specifics. So that means we need to learn and we need to know how the loading is connected in our IPS. So that means the main purpose of the planning is to make the system economical in terms of the cost, and then try to minimize the power losses as well. Right? So that we need what? We need the load survey and load forecasting, or sometimes we call it as a load prediction. So we need to study on the loading before we can design for the IPS. Okay, so these are some of the forecastings. The consumer, this is the type of the consumer. We have domestic is for the residential houses. The commercial, so commercial is like the shopping complex, university and hospital, the police stations, the hotel, and all the services. All the services is categorized in the commercial. And what is the industrial? Industrial consumers, normally they have the products, they serve the products, they have the manufacturing. For example, we have the SME, small and medium industry, we have large industry, we have the municipal consumer. This one is categorized in the industry as well. And the lighting, the waterworks, park, we have the garden park, or we have the agriculture consumers. So agriculture is categorized in the industry as well. And finally, we have the mining industries. Mining industry also categorized in the industry. Okay, I think you have very familiar with this one. So we have the primary substation, and we have the secondary substations. And the primary substations from, let's say, 132 kV, go down to 66 kV, and after that you will go to the secondary substations. Secondary substation is where we can get our supply. For example, in UTHM, we get the supply from 33 kV, just nearby the Pariraja here. And from there, we just go to the distribution substations. Distribution substations inside the UTHM, for example, inside the UTHM. Okay, but UTHM it is not the industrial consumer. It is commercial consumer. Seems like a factory. So inside the factory, you have a lot of the distribution substations here. So nowadays we are practicing 400 volts rather than 415. So 415 three-phase is the old one. Now we are in the transitions, in the transition from 415 to 400 volts, and the single phase is 230 instead of 240 volts here. Okay, you can read through these. Okay, so it's about the illustration just now. And when we're planning for the connections, so we need to bear in mind. Okay? So we plan for low voltage or medium voltage. Okay? So let's say in our factory we have medium voltage and we have low voltage side. So for low voltage side, so what is the consideration you need? Number one is the maximum power requirement in the kVA. So that means you have to gather all the loading, right? All the loading in the kVA. Okay, then types and the number of equipment. So what is the type and the number of equipment connected in our network in kVA as well. Another one is the shunt connected reactors and the capacitors as well. So the capacitor is normally for the power factor corrections, and the reactor is normally for the fault current limiter. The fault current limiter. So if it is connected in shunt and the reactor, it is used for the so-called the harmonics and the harmonics mitigations and the harmonic mitigations. That means we try to minimize the harmonics. So if the reactor is connected in shunt, reactor is some sort like the a coil. It's a coil. And for single phase 230 volts motor, so if the motor itself is greater than 6 kVA, if single phase, if three phase 400 volts, so if its rating is greater than 75 kVA, so that means we need to collect these data. Number one is the rating in the horsepower or kVA. Then number two is the type of control equipment. So what sort of the control equipments? And number three is the method of starting, and the starting current as well. So how many times of the starting currents as compared to the nominal currents. So the fourth one is the frequency of the starting. That means how frequent you start your motor. So let's say two times per hour, 3 times per hour, and etc. Right? So pardon me. Okay, for supply at higher kV, say let's say 275 up to 6.6 kV. So for all type of the load, so of course we need the P and Q. We need the data of P and Q. But for the model loads, so we need this all. So the control equipment, method of starting, magnitude, duration of starting, how frequent we start it, and under voltage setting, and what is the negative phase sequence protection. This one is for the fault, and the single phase or double phase fault. That means it's the asymmetrical faults. And the sub transient lock rotor. This lock rotor, that means during the starting capability. And another one is for the non-linear loads with harmonics current injections. We have a lot of the switching equipment that using the power electronics. So that's why with that we need to consider the harmonic current spectrums. For fluctuating load is sometimes you use, sometimes you didn't use it. Right? For example, the conveyor. In the conveyor, so sometimes we stop, or sometimes we off it, and sometimes we switch on it. So this is so-called the fluctuating loads in the IPS. So that means we need to consider. So how much is the changes in terms of the P, active power or the reactive power per minute? Then what is the shortest repetitive time interval? And the magnitude of the largest step changes. So how much is the P and Q in the largest step changes? So that is the concern. And next is the voltage sensitive load. For example, as I told you just now, the lamp itself is the voltage sensitive loads. So that means we need to cater this in our data collections. Okay? And another one is a shunt connected reactor and capacitor as well. Okay. So this is the worldwide voltage and frequency standards. So the blue color is same to us, which is practicing 50 hertz. 50 hertz. 50 hertz. Let's say 220 to 240. So it depends on your transformer. And the red color, red color is mostly to the Canada and the United States here, and Japan as well. And this one is Saudi Arabia, and one of the a very small country in the Africa here. I think it's Liberta or what, here. So they are practicing, including the Taiwan as well. They are practicing the 100 volts 60 hertz. 100 volts 60 hertz. So just a small area only, as compared to 50 hertz. So most of the world country are practicing 50 hertz, 50 hertz and 220 to 240 volts. So just a parts of our country, like our neighbor, Philippines and South Korea. So they are practicing 60 hertz, even though the voltage is the same, same to us, but the frequency is 60 hertz. So it is more or less depends on where you buy the transformer. If you buy the transformer from a European country, then of course it is 50 hertz. So if you buy the transformer, for example, the Philippines, they normally partner with the US. Normally they buy a lot of the transformer from US. That means they are practicing 60 hertz. Okay, so this is more or less about the IEC voltage standard. So we are here. So we are practicing the 50 hertz and 230. So that's why you got a description here. We are still under transition from 230 to 240 to 230. Okay, so this is the tolerance. So when we design for the IPS, so we need to bear in mind. So it depends on the voltage level. So normally IPS will be at this category. So it's from 33 kV to 400 volts in the three phase. So it is divided into two. One is a steady state voltage fluctuation, which is a normal condition. So this is the variations. So 400 volts. That means the upper limit is maximum 10% only, and the plus 10%, and lower limit is minus 6% of the voltage variation. So that means the voltage, let's say 400, so you just can minus 6% only for the lower bound. Okay. So for the rest of the kV, so the allowable voltage variation is plus minus 5%. But during the contingency means during the faults. Contingency conditions, so all the voltage level will experience the same percentage of the variation, which is plus minus 10%. It is higher. then frequency is 50 hertz. It's normally is 50 hertz plus minus 1% only. And so this is for British standard like us, and 60 hertz is for the US standard, also plus minus 1%. Because frequency changes is very crucial. So we are not allowed the frequency changes like the voltage can up to 10% or 5%. No, so if the frequency is up to 5%, that means you will experience a very bad situations in your network. So because the frequency is dealing with the time, and frequency is dealing with the time. So any controller in the factory, for example, in the factory, so we use the PLC, we have the timer. So all the timer is depends on the frequency. So if the frequency is very too much, let's say 5%, so you will have a very chaotic condition in your factory. So all the timer gone, all the controller gone. Okay, the next is the distribution classification. So it's according to some criteria. So one is the nature of the construction, overhead line or underground. And if according to the nature of current, you have a DC or AC. So most of us we having the AC only. And number of wires. So we have how many wires? So in our practice we have one phase, two wire, neutral and live. So for three phase we have practicing three phase, four wires, RYB and neutral. And if the distribution system is according to the scheme of connection, so we have radial, ring and interconnected, or the loop also. So these are some of the standard and some of the capacity. That means the installation capacity. For example, 33 or 11 kV. So it can be up to let's say 5 MVA. So anyhow, it depends on the practice of that particular country. So it is not fixed. At TMB, we have our practice. Later on, we will see 33 kV, or if we let the our power, that means we get the power from 32 kV. Okay, how much is our maximum loading? So if we take from 11 kV, how much is our maximum loading we can go? If more than that, then we have to upgrade our kV. Then we have to require the TMB persons, require TMB person to upgrade it. So as I told you, we have three types. Radial, loop and rings. Radial, loop and rings for the distribution line. So radial, of course, it's just a straight line like this one. So if you have something happen here, then all the connected loads here will be gone. So this is the disadvantages of this radial. So of course the advantage is the cheaper. Is the cheapest configuration. Right? And the loop, so loop is like this one. You loop everything here, but the source is still from one source only. So you only have one incoming, one source, but you loop your distribution substation into like this one. So let's say you have fault here, so the CB circuit breaker here will trip, and the circuit breaker here also will be tripped. And where it get the power, so for this sub distribution, you will get the power from here, and at the same time this one also will get from another loop here. So that's why this is the advantage of the looping. But the disadvantage is when you have the fault here, secondary substation, you have the fault, so everything here will be gone. So this is the disadvantage of the loop. So the most reliable is the ring, because the ring you will have at least two source, two incoming. So if something happened here, like just now, if something happened here, we still can get the power from another secondary substation. So this is the beauty of the ring. The beauty of the ring. So this is the most reliable among these three types of the configuration. This is normally practiced to a very sensitive, not sensitive, is very reliable area, like airport, The airport is normally they will use the ring. That means they will have the alternative source coming in if something happens to one of the source here. So you can read through the text. I don't want to repeat it. And this one actually is a secondary distribution line. This one is inside our factory buildings. Inside our factory building, like just now, what we are talking just now, the primary distribution is at the outside of the factory. The outside of the factory. This one is inside the factory. So same thing happens. So it will have the so-called the radial. So it have the loop as well. Like radial, we have loop as well. But here we don't have the ring. We don't have the ring because why? Because not all the factory will have backup supply. The backup supply. Normally the ring, one of the supply is taken from the backup supply, which is the captive generation. Right? So that means in overview we don't have it. We only have a network system. We bank it. So how to bank it? It's not like the capacitor bank. The bank here is not a capacitor bank, but rather we bank the transformer. The transformer. Okay, radial is a common one. Radial. So if anything happen in this line, everything will be gone here. Okay, so that is the radial, and you have the expanded radial like this one. You can expand it like this one. So if you have the transformer here. Right, so normally we take this one is incoming from TMB, for example. Okay, we have the distribution transformer. Then we only go to our switch gear. So this is our switch gear, and then it will fit to the rest of the load center in our factories. Okay, so if we wanted to expand the radial, so we just simply take it from this one before the distribution transformer, and then we just expand it to another. So this is the expansion, the expansion of our factories. So another one is the loops. Loop. So if something happened here, so we still can get the supply from here through the switch here. So if the fault happen here, so this switch will be closed, and we will get the supply from this area, from these directions. Okay, so this is the beauty of the loop system. So you can have like this one. It is interrelated like this one. Okay, so it's a looping. So if something happen here, this one will be connected. So this one will be connected. So in the normal case, so either one only will be operated. Either one only will be operated. So this one is a non-parallel operation and non-parallel operations. So that means it depends on the needs only. Let's say if something happened here, then this one only will be energized. Okay, the bank. Okay, just now we're talking about the bank. It's not about the capacitor bank, but rather we bank the transformer like this one. So that means we have alternative. Sorry. So that means we connect several transformers. Pardon me. Okay, so that this one is about the reliability cases also. So that means we have something happen here, then this one will be activated. Okay, and in the normal cases we can have the parallel running transformer. I mean this either two transformer can run in one same time. Okay, especially in the factory, let's say one part of our plant is going to have the maintenance, and that means we switch off this one, and then we can get the supply from another one. Okay, so this is the bank. So it is very reliable. It's a very reliable supply. Okay, so you can have like this one, right? So this one is interrelated also. So as I told you just now, if we have this is plant A, this is plant B, so we having a maintenance at plant B here, right? Then we can we can disconnect this one and disconnect this one, so that we just focus on here. Okay. This one is when we have a spare, the sparing transformer scheme. So that means this one is not operates, and this is just for the spare purpose only. Only these three will be operated. Okay, this one is just spare. In case one of it will it's happened something, right, at one of the transformer here, then we only switch on or energize this transformer. Okay, I think we stop here.